get started then. So thanks everyone for coming. This is a talk on fault tolerance in Apache Spark. My name is Imran Rashid. Actually, it's a little bit more general. It's really fault tolerance in distributed systems in general, looked at through the lens of Apache Spark. It's kind of both a mouthful and too long to fit nicely on a slide, so I just cut it down for that. Quick reminder to use the app to rate sessions. I know I would appreciate it. I'm sure the conference organizers really appreciate it. It's a brief outline of what I'm going to talk about in this talk. So we're going to start with just a very quick overview of Spark, its computation model. What does fault tolerance mean in general? And I want to talk, again, more than just about Spark, but whether you're a user of Spark or a different distributed system, or maybe you're developing your own distributed system on top of a cluster or whatever else, I think there's still some important lessons here that you can learn from what Spark has gone through. So we're going to do that by examining specific scenarios with Spark, kind of what was designed, where things have worked, where they haven't, and finally at the end, hopefully get some key lessons learned. So a little bit about me. I've been a user of Spark for a long time. It was v0.5, and I think like nobody else really was using it at that time. And it wasn't even an Apache project yet. And that was actually how I got introduced to Scala. So after using Spark, it was so early that I kind of just started making fixes because there were a lot of things broken. It was exciting, but lots was broken, and that led to me being a committer and a member of Apache, the PMC for Spark. Now I'm an engineer at Cloudera, where I work on Spark all the time. And since this is a Scala Days conference, a bit of other stuff, I've been a user of Scala for that time as well. And nothing to do with Spark at all, but I also wrote this arg parsing library called Sumac, which I'm just going to make a quick plug for. Probably everybody writes their own arg parsing library, but hey, if you're interested, then I think it works. It's not active because I just still use it and it works for me, and I know of others who do too. So you can check it out if you like. Okay, so I also want to find out a little bit about the audience. How many people are using Spark? So how many folks have written Spark jobs? Okay, everybody. How many folks have Spark jobs in production? Okay, that's a good amount. How many of you have a Spark job in production on over 100 nodes? Okay, that's actually still pretty healthy, but it's definitely thinning out. Okay, cool. So let's start with a recap. This is hopefully very, very basic for most of you, given the background of this audience. But quick recap of Spark's computational model. And maybe some folks are familiar with MapReduce. If they don't know Spark, it's very similar. The basic idea is you have some giant data set, which is split across many nodes in your cluster, and you want to leverage your entire cluster to compute on it. So you split data into partitions. And the idea is that each partition can be computed entirely independently of the others, right? So this is great for distributed computing. The less coordination, the easier this is. One node just has its data, it just does whatever it needs to do, boom, there's no coordination whatsoever. That alone is too limiting, so just like MapReduce, Spark has this idea of a shuffle. And so that's when you say, okay, now I need to group data by my key. So if you're dealing with like transactions, maybe you want to group by the day of the month, right? So you get all the data for a certain day. Or maybe you want to group data for a certain user or something like that. And then you can compute on aggregated data. And this operation is called a shuffle. And those are really kind of the two cornerstones of how computation works. And again, this so far is exactly like MapReduce. But Spark took the idea just a little bit further in a couple different ways. So one, it pipelined operations together. So if you had a map and a filter and another map, Spark would just realize, hey, I can just do those in one go. There's no reason to ever hit disk or anything. The other thing is you can do many shuffles in a row. So you don't, if you want to do multiple different groupings, you don't need to do the grouping, write all the data to disk, read it back from disk again, do another shuffle, et cetera. Something to go along with that is Spark does this. You get fault tolerance via lineage. And I'll explain this a little bit more. But so MapReduce, the idea was you would get fault tolerance via replication, meaning that your data was always in multiple places. So if you lost data in location A, you had some master which would know, hey, every piece of data is stored in multiple locations. I just need to go figure out where else is this data located. Spark does something very different. So it assumes there is some resilient data store like HDFS out there, right? Which will probably use that kind of mechanism. But Spark, it doesn't necessarily have a copy of everything along the way. The idea is that errors are, though you certainly need to handle them, they're not that common. And so let's optimize for the happy path. Instead of making 99.9% of our work go through this really expensive thing. Let's make that tiny fraction just do a little bit of extra work. Still be correct and sound, but not go through, but keep things faster when we can. So how does this work in practice? Let's say that we were computing this, and then suddenly something goes wrong with node A while we're in that final step. And so obviously, you've got to put that final step of work, that part 0 and part 1, on some other node. And so just to keep the example simple, let's say we move it onto node B. But you'll notice that there's input data for those parts, which reference the previous step. And some of that data lived on node A. So Spark says, oh, hey, that data wasn't replicated, because I don't do replication for all my intermediate steps. So instead, I need to regenerate that data. So it goes back that step. It also assigns that data to another node, regenerates that, and moves on. By the way, one thing I should mention, so these arrows for shuffles, I got a little lazy with drawing them all, but really that's an all versus all thing. Every piece of data on the right side depends on every piece of data on the left side. So this is a very complicated operation, and that's why when something goes wrong, you may have to go back and compute everything for whatever is still remaining. So let's look at a slightly more complicated example. I said that Spark can do many shuffles in a row, so how does that work? So say there were 3 shuffles, right? And when you're in that final step, something goes wrong with one of your nodes. Well, we're going to start doing the same thing. We'll assign both those last tasks, which we lost, to node B and the step before, right? But now when we're computing part 0 on node B in the middle step, well, that depends on part 0 from the very first step. And we don't have a home for that either. That data's been lost. So we need to even assign that somewhere else. So you reassign that data to node B. Again, it could be anywhere, but just for the purpose of this diagram, we're going to say it assigns it to node B. And now Spark executes part 0 and part 1 on the first step, on the second step, and on the third step. And those all have to occur in sequence now, right? So this is more expensive than if you just went back one step and said, oh, I have a replica, right? Let me just read from my replica. But on the other hand, it means that when you don't have to write replicas, it can all go much faster. And that's the trade-off that Spark made. And again, this is contingent upon the idea that eventually at the very, this could go back many more stages. At the very beginning of it, you have some data store which is actually doing the replicas, or some other mechanism of ensuring you do have a reliable copy, if a node went down. People might be here because they're super excited about Spark. It's a hot topic. There's lots of cool things. It's a streaming engine, SQL. It does machine learning. It does dynamic allocation. It adjusts resource usage based on load. It's doing vectorized computing now. It's got a query optimizer. It won this gray sort benchmark. Who knows? Soon it's going to be doing LLVM maybe, and why not? Maybe we'll get quantum computing in there. It's going to do everything, right? So sorry to disappoint you. None of that is relevant for this talk. I'm not going to talk about any of that whatsoever. I'm going to talk just about fault tolerance, which is probably the stuff you took for granted and you thought Spark solved long ago. But again, hopefully this is useful for more than just Spark, for whatever distributed systems you're thinking about. Okay, so fault tolerance. It was, again, everything which I've described so far about fault tolerance, this is what was designed from the very beginning of Spark. It came out of this research project at Berkeley, and the very initial paper says exactly what I've described, more or less. So there's nothing has changed in all those years. And in that time, Spark's been used and tested a lot, right? We know it's been deployed in a lot of different places. And basically, it's kind of just worked, right? We haven't encountered any bugs so far. There haven't been any regressions, and it's all just worked flawlessly. Oh man, that went pretty fast, but if you guys can rate this, I'd appreciate it. Thanks. No, okay, so I'm just kidding, obviously, right? That's not the story at all. There have been plenty of problems, despite that simple model. And so I want to talk about, well, where did we go wrong, right? So Spark 2.2 is going to come out soon. The branch was just cut recently. And we're still fixing issues. I mean, this is what I spend a lot of my time doing. And for the most part, they're old bugs, which we're just discovering, despite this history of it being this project which has been out there, and this research project written by really smart people and lots of people looking at the code and running it. You know, when there are regressions, it's not like, oh, it was a regression which was just introduced by accident really late in the 2.1 release cycle, and oh, we'll fix it for 2.2. It's more like it was a regression introduced like a year ago, and just nobody's noticed it until now, right? Oh, all of a sudden we realize it's happened. So I want to think about how did this happen by examining a bunch of different cases. And you know, there's too many for me to cover them all, but hopefully it'll be a little smattering of different concepts. So the rest of this, most of the bulk of this talk will kind of be jumping around different concepts, and I hope at the end I'll be able to tie it together. So stepping back a little bit, I just want to talk about what fault tolerance even means, right? So folks who are using Spark, what do you think Spark is going to recover from? So here's a list of a bunch of different problems. Or if you're building your own system, what do you think it's going to recover from? I mean, you can read about any of the new distributed system technologies. There's lots of them out there. They'll always mention something about, oh, and we're fault tolerant, or whatever. And I always just wonder, what does that mean now that I've seen how Spark does and doesn't deal with fault tolerance? And so it's really something you should be thinking about. What do you want your system to be fault tolerant to? So node failure is kind of the example which I talked about so far. Just imagine like someone yanking the power cord out of that box, right? Okay, yeah, it's just gone. Like, you know, you can't do anything with it anymore. But you might have flaky hardware. Maybe only the GPU is bad on that box, or the network card. The most common case is like a bad disk. That's what we see the most, really. You know, it's a special case of flaky hardware, but so common I think it's worth talking about. Another example is slower nodes, right? What if, you know, for whatever reason, one node just it's not the disks are not spinning as fast, or there's bad firmware, whatever it is, right? Maybe so Spark is a general framework for programming. It's not like one program. Users submit code to Spark. So what if there's an error within user code, right? And so this goes on two sides. I've had people literally, like, they've had like just a straight up exception in their code, like they wrote bad code, and they're like, but Spark is fault tolerant. Shouldn't that, like, can it take care of this? I'm like, how is that possible? But while that's ridiculous, I think something which people are more surprised by, reasonably surprised by, is they have their code, it runs perfectly well for weeks, months, right? And their Spark job's running happily in production, and then suddenly tomorrow it fails with incomprehensible errors. Like, well, what's going wrong? My code was working. Well, your input data changed somehow. You know, today it's got more skew, and now Spark can't handle it. Network partitioning is another one. So this is really important if you are thinking about like the distributed data stores. This is like if there's all these discussions about the CAP theorem. I assume this is something that Cal Kingsbury is going to talk about tomorrow. And then the last one. This is like, what if there's some cataclysmic event, right? And this, okay, obviously that last one's kind of a joke, right? So you know Spark's not going to recover from that. But on the other hand, I think it's worth mentioning just because sometimes people think, well, this should be fault tolerant to everything, right? I just want fault tolerant. It doesn't matter. Like, my system needs to be robust, right? And you know, maybe if you're Google, you do need to care about, like, okay, what if there's a cataclysmic event in New York? Google still needs to be like running or whatever, right? But for a lot of people, you need to be somewhat realistic, right? How much fault tolerance do you really want? How much downtime do you expect each of these to cause? And I'll come back to this idea about, you know, which of these you're going to pick and what does that really mean. By the way, folks can interrupt me at any time if they have questions. So one of the ways that you can be fault tolerant is just to fail fast. So this sounds kind of ridiculous, right? Like, that's not really fault tolerance, right? Why like failing? That just sounds like the dumbest thing you could do. But it actually kind of makes sense, right? And the reason I say this is, think about the question you shouldn't be asking is, I just want to be fault tolerant. Am I fault tolerant to everything? You should be asking, well, what am I fault tolerant to, and what's the price I pay when that fault occurs, right? And so if it's very fast for you to restart, and that'll solve your problems, then just do that. There's no reason to be thinking about anything more complicated. And it's interesting because actually, for a long time, this was broken in Spark. Spark basically had an infinite retry. So anytime there was like a failure in a node, it would go back and run the previous step. And after it succeeded, it would go to the next step. And if they had another failure, it would go back and try it again. And just keep doing it over and over and over. And you know, you might think, well, how likely is it you're going to keep having nodes failing over and over and over? So so this was actually really bad because Spark had a bug which caused it to do this. There was no node failure. Spark just got confused. Its internal state was messed up. And it just, because it kept retrying, it never kind of got to clear its state and have a fresh start. So a fail fast would have been much, much better. And so I actually have to tell you a a little story as a user. But so when I was, and then in the early days of me using Spark, right, it was at a small startup. And we were very much just trying to get products shipped out the door, right, for constantly pivoting and figuring out what would work. And we ran into problems where we would see Spark just seemed to be in very strange states. We didn't understand why it was running the tasks it was running. Nothing made sense. And the thing is, it would often work reliably, but then one day a week we would wake up thinking that, oh, it's just going to work tonight, and it wouldn't. And our thought was, it must have been some misconfiguration on our side, right? Clearly we were using it wrong. Spark's this brilliant system designed by great people. So there's got to be some misconfiguration on our end, but we also didn't have the time to investigate it, right? It was like, I just got to get this thing done. So we literally wrapped every single Spark application we had with what we call the watchdog. If I knew the program took 4 hours usually, after 6 hours, I'd just kill it and restart. And we did that all over the place. At the time, it felt like this really dirty hack. And then as I've kind of dug more into Spark and seen how many errors, how many issues there have been, especially at the time. I mean, this was when Spark was way more buggy. It's like, thank God we did that, or else it would have been really hard. There was no secret configuration which would have solved our problems. So again, if you're using Spark or not, I think it's important for users of distributed system to be somewhat suspicious of the claims. Don't just be happy they said, oh, we're fault tolerant. Well, I can check that box and move on. What are they fault tolerant to? How do you know they're gonna hit that? Another thing to think about is, so I made it sound like this is the perfect solution, but it's not necessarily, right? Just because you restart doesn't mean it's going to work the next time, right? So the problem I presented was when Spark's internal state was messed up. But what if a node was bad? If the next time you tried to reuse that bad node, you wouldn't be in any better situation. So obviously, this is something that's useful, but you still have to have some reason to believe it's going to work the next time around. OK, so going back to this idea of how things can fail. So again, right from the beginning, Spark was designed to recover from failed nodes. There were unit tests in the code base, which ran on every single check-in, right? There are live tests in the sense that, like, we spun up clusters and we checked what happened when we destroyed one of the nodes, through containers and stuff. It had plenty of time in production on large clusters where things actually went wrong, and it seemed to work. There's a really fundamental problem, which was that, again, kind of it following this path of like research paper and then suddenly becoming huge. It's like, well, in the research paper model, you can just be like, well, the node's either alive or dead, right? Those are the two states. And it's actually not like that at all. You could have flaky hardware. And disk corruption or a bad disk are by far the most common. And we've actually encountered cases where you would have a cluster of 1,000 nodes, which is however many 10,000 disks or so. One bad disk effectively took out the entire cluster. And that sounds like a crazy claim. So I want to walk through how this happens. So let's say that here's a diagram of Spark doing some scheduling. So let's say it has this big stack of tasks it's going to schedule and some set of nodes that it has with slots to run these tasks on, each of them with multiple disks. And you can imagine, of course, it being many more than 4 nodes, but just for the purpose of the diagram. So what does it do? OK, it pops tasks off the stack and sticks them on those nodes and starts running them happily. Now, one of those nodes, a disk goes bad on node D. OK, so those tasks are going to fail because this disk is bad. It's going to try to access the disk or whatever. So this is actually OK. Spark understands how to cope with task failure. It knows things will go bad. So it takes those tasks off, puts them back on top of the stack. It marks node D as having empty slots again. And then it says, OK, well, now I've got to find let me see, can I schedule any more tasks? All right, let me look. I do have things to schedule in my stack that's not empty. Let's see, do I have any place I can run those tasks? Oh, I see, node D, perfect. Let me go stick those tasks back there again. Uh-oh, they failed again, right? And this would just happen over and over. There was no protection for this kind of thing because node D still was responsive, right? It was sending back heartbeats, it was sending back metrics. Sometimes tasks would even succeed, so I presented this in a very simplistic way, but because it was one disk out of many, sometimes some tasks might not hit the bad disk. And so every once in a while, a task would succeed, right? And so this took out a large cluster from one bad disk. So it was not a happy customer about that. So I'm referencing JIRAs here, by the way, if anyone's curious about more detail, and just if you're interested later on in looking this up. So this was complicated to solve in Spark because Spark is such a general framework. It took these ideas of MapReduce and it said, MapReduce is so restrictive. We can do something better than that. We can release these restrictions and we can give people more power. But that means that people run a huge variety of workloads. Sometimes the workloads are really big production ETL jobs, which each task takes hours. Sometimes it's ad hoc data science jobs where the code that's submitted is like bad 10 times in a row until the user hacks on it, and then suddenly they get good code. Sometimes the hardware isn't going to show up. Like there is bad hardware, but every single task isn't going to trigger it. And maybe it's one bad disk, maybe it's a bad GPU. And there's also just like truly transient issues. GC pauses can appear to be like bad hardware. Maybe the network is swamped. You can't really tell what's going on, right? So fixing this, it sounds like an obvious problem. Oh my God, how could Spark be this dumb? It was actually really hard to solve. It involved several committers. There was an extensive discussion between me and some of the other folks that know this code pretty well in analyzing each of these workloads and be like, well, what do we do in this scenario? Oh, that sounds like a good solution. But wait, what if you have a streaming Spark app? Then it's not going to work so well. The error reporting is going to be very confusing. And it ends up meaning that you have to make a lot of compromises. And sometimes including a lot of configuration knobs. And we believe the solution is pretty good out of the box, but it also might mean that users need to do some custom configuration. So again, if you're building a system, then if you can make your system simpler, then a lot of these complications become easier to deal with. You still might have to deal with this problem of flaky hardware, but it might be much easier for you to handle. So after encountering this issue, I still really wondered, how is this possible? Are just disk failures super rare? And it was hard to find really, really good evidence about this. So if you read early discussions in MapReduce, they make it sound like issues are just constant. Like you can't do anything without something going wrong in your 1,000-node cluster. But we know folks now are running 1,000-node clusters, and they had been running for months before they suddenly encountered this bug and had issues. They kind of just hint at this in the language that's used. And so I have a link to this article, Data Corruption is Worse Than You Know. It's actually, despite that title, when I read it, I was like, oh, it's actually not that bad. So I think hardware probably is getting better. But it's there, right? So this article was interesting because it was from CERN. They basically, they're generating like petabytes of data constantly and, storing all these disks, and some folks, they went around, and after a while, they actually analyzed, well, how much data was getting corrupt? How many times did we lose disks? How did this correlate with what manufacturers were telling us? And yeah, there definitely were failures, but it also wasn't sort of cataclysmic. But there's other reasons why you really need to deal with failures in large clusters. So first of all, maintenance is constant, right? If you have a 1,000-node cluster, almost all the time, some DevOps person needs to take some nodes out of the cluster and replace some hardware, because they're always adding some nodes. It's not like they buy 1,000 nodes at once. They leave it for a year, and they're like, okay, we're going to buy another 1,000 nodes. Like they buy 500, and they're like, oh, we have budget to buy another 200, and then we have budget to buy another 100. And so you end up with this heterogeneous mix, and they slowly start phasing in and out and upgrading some nodes, removing other nodes. They do a test where they remove some nodes, put it in a small cluster, try upgrading some firmware, and see whether it works, right? There's just this kind of thing happens nonstop in a big cluster. And there's so many people using the cluster at the time that the users just need to not know about this at all. They can't bother coordinating with users. Maybe you think, well, I'm just a cloud user. I don't care about this. Like it should all be abstracted away from me, right? You might be interested in Spot, because obviously that's more cost effective. But that means that your app might happily be running on 20 Spot instances for some amount of time, and then suddenly half of your Spot instances get yanked away or more. Okay, so jumping to another case. So Spark introduced this interesting bug in coordination of error handling between two components. So on the left side is sort of the core fault-tolerant logic that had existed for a long time. There's this try-catch block. What goes on inside the try-catch block was sort of the work of the task. And if there's a specific type of exception, then Spark knew a certain type of fault had occurred, and it would take some recovery Now, there's been a lot of action in the SQL part of Spark lately, and so this code on the right was written relatively recently. They also had a try-catch block, and they said, oh, well, let's do something defensive here. This is kind of new code. Let's be safe. If there is an error, let's give the user a little better error message. I mean, I didn't put that all there just to keep the example short, but they wanted to sort of tidy up what was going on there. So they said, okay, any exception, we're just going to wrap it in our own type with a little extra, a better error message. Okay, the big problem here is now Spark exception is not a fetch failed exception, right? And so the error handling has gone away, right? So now that the outer failure handling no longer knows that this was going to happen. So when I saw this, at first I was like petrified, like, oh my God, how did this go in? And then I stepped back for a second and I examined when exactly this could occur. And I realized, first of all, it could only occur in a pretty rare workload. So that exact block I'm showing on the right is in a certain type of function which most people never use. It is used sometimes, but not that much. And secondly, if you are using it, the failure has to occur at the exact right time. A whole bunch of work has to happen in the beginning of the task. You have this super narrow window where if a failure occurs right then you're going to get the problem. Then there's this other long section, and again, if the failure occurs in either of those two much bigger time chunks, no problems at all. So I felt a little relieved. I was like, you know what? No one's ever going to actually hit this. Yeah, actually, this got reported to me because somebody did hit it. But I was like, this is like, a crazy, super rare event. I'll fix it, but no big deal. And then I thought about this some more, and I decided, you know what, actually, I probably should be panicked about this. This was really, really not great. So just think about, again, what happens on a 1,000-node cluster. You've got 5 to 10 processes per node. Nodes are now pretty beefy. It's like 32 cores, several hundred gigs of memory, so you want to split those into multiple processes. You've got a bunch of users on that cluster. They're all doing their own thing, right? All running totally different types of apps. Wildly different workloads. Each application is going to be running shuffles constantly. So you're definitely within sort of one user's application, it's going to have maybe 50 nodes it's working with, and those nodes are all talking to each other constantly. Every shuffle means they're all talking to each other. And meanwhile, again, DevOps is doing their cluster maintenance. So you've got, when they yank those 10 nodes, there might be like 10,000 processes talking to those 10 nodes that you just yanked. So it's actually, there's a pretty good chance you're doing this rare stuff when this happens, right? So really, it's hard to feel confident when you see this kind of problem. So we realized that this wasn't good, right? This is a bad situation, and I think the right solution is to have more tests. And I'm really excited that in Spark 2.2, the community as a whole has realized it's a problem, and we're committed to getting better unit test coverage. The goal is 98%. It's like the metric is a little below that right now, but we're going to be right around there. And I feel pretty good that there aren't going to be any problems from now on. Okay, more baloney for me. Okay, that's not true at all. Not only we're not even trying to achieve a unit test coverage metric. So first of all, unit tests wouldn't have caught any of the problems I've discussed, right? You wouldn't find out there's a problem with handling flaky disks if you don't have a unit test to check for flaky disks, right? No one was even thinking about that problem. Now, again, I don't want to make it sound like I don't believe in unit tests. Unit tests are super important. And in fact, I feel like 90% of my work as a reviewer is often to take someone's patch, which is often correct, right? They'll note the change. You're like, oh yeah, we should remove the race by reiterating this or adding a lock. I'm like, no, we need to write a unit test. No, it's too hard to write a unit test. It's this real race. I'm like, okay, fine. I go write the 200 lines of code, which are setting up the mocks and making sure I get the exact right sequencing and everything. And that's important for regression testing, right? So that we know that we're not going to reintroduce this bug again and again and again. But it's also, it's just not going to solve this problem, right? I don't see a way of us having unit tests to cover every possible scenario, every possible interleaving of events. That's not going to happen. Okay, so a better answer might be fault injection testing. So I think the most well-known example of this is Netflix and their work on Chaos Monkey. I think that's gotten a lot of attention. Basically, what Netflix would do is they would, even on their production systems, they would just run something to intentionally cause faults. The point being that this way they would discover how, if they're already causing faults and their system survives, then if a couple more happen, they already know they're relatively robust to it. This helped them find issues, this helped them gain confidence. And in fact, they did some tests on Spark, and they blogged about it. So this linked to a post from back in 2015, specifically on Spark streaming. So, you know, this is definitely good. I think this is great. But when that post came out and I was reading it, it was interesting because basically they said, oh, we did all these tests on Spark streaming. We found a couple minor issues, but those got fixed quickly. It was nothing really serious. And they said Spark streaming passed with flying colors. And I was at the time solving like 3 bugs in fault tolerance. I thought, okay, this can't be, again, this isn't doesn't sound great either. And the reason is that you need, for fault injection testing to work, you both need the right type of faults. Again, are you actually testing a flaky disk and not just like a node which is removed completely? Do you have the right workloads? Do you have that one strange operation which, you know, only 0.5% of users are actually using? And are you doing it at large enough scale that you get the exact right timing? And this is not to criticize Netflix. Again, like, I think it was a useful thing they did. But you shouldn't read that blog post and be like, oh yeah, great, they did it, we're the end of story. Now we know this app is safe. Like, have you covered these 3 axes? And as well, totally not to criticize Netflix, I was doing kind of the same thing internally as I was trying to unravel some set of bugs. There was a very complicated fault which I couldn't quite get my hands around. I understood one issue, but my test to fix it didn't seem to quite work. So I wrote sort of a little mini fault injection thing, where I ran it I set up a small cluster and I ran it for like a day or 2, I forget, where I was injecting random faults in it and, you know, saving the log so I could go dig through it later on. And I found not only the one issue which was confusing me earlier, but I found a second issue too. So I found 3 bugs in total. I was like, oh great, this is like fantastic. My fault injection system has worked. And I was feeling like, you know, like I had done something super awesome. Like now I could feel really confident about fault tolerance in Spark. So I went and I thought, well, let me just see, like, this is probably going to solve all the fault tolerance issues. I'll file this issue, and let's just see what else is out there. But like instantly, as soon as I did a search on Jira, I found there was already another open issue which someone had filed and relatively with a detailed explanation, which my system hadn't found. And I had the right faults, I had the right workload. I just didn't have the perfect timing, right? It was just, I just didn't have enough coverage to create that issue. All right, so to keep this all in perspective, you should keep in mind my job is basically to look at when things go wrong, right? Support people on these large clusters and deal with these really hairy internals. So I have been telling you about all the ways things can go wrong. Spark is used successfully in a ton of places, but and again, I think what's more important is to think about sort of the maturity of a distributed system. I don't see any other system is going to escape some of these issues. And so in a way, it's almost good that Spark has kind of lived through this stuff and we're ironing out these issues. Then again, it's also like, well, we might need to do some big refactoring, and so how many of these are we going to reintroduce? And so that's even, there's continuously discussion about how to handle this as we make changes to do it safely. Also, I'm going to make this somewhat bold claim that certainly all the bugs aren't gone, but I feel we're definitely moving into a territory where it's more likely the user is doing something wrong than you know, a fault tolerance happens in the exact wrong way and everything that you get this terrible event. You know, I can certainly see me, if I was writing some Spark app late at night, hacking away and being like, oh yeah, my code's fine. I don't need to go through code review. I'm just going to check it in on the projection job, not worry about it. It'll be fine, right? Simple code. It'll be something stupid, right? Where I don't think through what's going on. It works on my unit test, but it's actually it's not really the true scenario. Okay, so to close, a couple of different lessons to tie it all together. So keep in mind there's a lot of different types of faults possible. I didn't even really cover them all. There's, you know, races, there's consistency issues, there's network partitioning, there's what if there's a fault in the system you're built on, all sorts of other stuff like that. Things can go wrong in many different ways. And the testing is really hard, so if you are, you know, like, oh, I'm going to build my own fault tolerant system, just, you know, maybe think about what you're signing up for. But maybe if you're going to build it so simple, maybe it actually will be easy for you to get the kind of guarantees you want, right? Yeah, and so again, whether you're a user or a builder of a platform, you should really think about what do you want it to guarantee, right? One is just, okay, if it fails, I'll just restart, right? One is sort of that simple watchdog. When is that good enough? Maybe it's good enough in a lot of scenarios. How do you know your system is actually delivering what it's saying it is? The worst case would be is if it reports success, but something has gone wrong. It's like missing data or something like that. And again, would something simpler be enough? Finally, to go through that list again, now that I've been through some of the examples in Spark about, again, I just want everybody to think about, for your app, which of these things do you really want fault tolerance for, right? So we said Spark now handles node failure, flaky hardware. Slower nodes, actually, interestingly, in Spark is a whole different category. I didn't talk about it here. So that's more covered by something called speculative execution. There are other ways you could potentially handle it. Yeah, and again, network partitioning and some sort of larger cataclysmic event, those are not handled by Spark at all, right? So Spark is not going to deal with network partitioning, though if you talk about fault tolerance in distributed systems, especially like data stores, that's kind of where people are talking about, because that's the really hard problem. And Spark doesn't even touch that, right? It says that's like some other thing is responsible for that. I'm dealing with just an isolated compute component which lives for not that long a time. If there's partitioning, whatever, right? Yeah, and I talked about errors within user code. And this is, I would probably call it to be more like robustness and not necessarily fault tolerance, which is if data characteristics change, is your app that seemed to be fine suddenly going to fall over, or is it going to gracefully degrade? Great, and that is all that I have. So thanks. Any questions? For real this time, no joke.
Hey, so I've run into like a scenario a couple times where I have a moderately sized cluster of like, say, 300 instances, and one node will, say I have like a stage with like 4,000 tasks. One node will just, 8 of those tasks will just take forever. And I can see that it's that node, and if I find that node and I go on EC2 and I just terminate it, then it's, everything completes immediately.
Yeah.
You mentioned something like briefly at the end, the speculative execution. Is that something? Is that what you're?
Yeah, that's
Can
was
you
exactly
talk
going to be
about
my
that?
yeah. So the idea with speculative execution. So this is an idea borrowed from MapReduce. Actually, it's not something new to Spark, but it's to deal with this scenario of slow nodes. Like you might think like ideally this shouldn't happen, right? Why? I've got equivalent hardware. It shouldn't happen. It happens for real all the time. I mean, reasons range from like the firmware is wrong on some machine, or I mean, sometimes who knows why? I don't know. But it happens, and the system should deal with it. And so the idea behind speculative execution is if after some portion of tasks have completed, and you have some that are still running, you say, well, look, these have taken, like as an example, let's say you configure it to be like after 50% of my tasks have completed, and then any remaining task which runs twice as long as the median time so far, I'm just going to say something is wrong. And so I'm going to run another copy of that exact same task on some other node. And now they are going to race to complete. And I will handle that race at the end, right? Whoever finishes, then they have to coordinate with some central location. And so then Spark manages how to deal with these two completing. And whether one completes and the other doesn't, they both complete at approximately the same time. It should be able to sort that out. That said, this feature is actually something I often don't recommend to customers that expect really good reliability. Not necessarily the fastest runtime, but really good reliability, because it has been somewhat buggy, and I don't think it's gotten the love it deserves. I actually it's not like I can point to specific issues, but when bugs are fixed in it, I am kind of shocked. I'm like, wow, that looked like a really basic bug that was just fixed. So it just seems like it hasn't quite gotten as much love as I feel like it should. But by all means, like if on the other hand you're like, well, I'll just deal with that. If the thing crashes, then I'll just run it again, and I'll deal with a fail fast kind of scenario. But then I think you can definitely go for it. It's just some configuration. I forget the name, but if you look in the docs, it's like spark.speculative.enabled or something. Right. Well, so basically, then the second copy is just also going to run slow, right? So I didn't mention that. There's another very good explanation, which is it's your fault. You have written a task which is slow, right? And I'm saying you as in you personally, but it might be, oh no, it's my input data's fault. But as far as Spark concerned, it's your fault, right? As the application developer, and Spark won't do anything automatically about that. Now there are things you could do better, like, well, let me look at task metrics to see, well, is it data skew? Are these tasks taking longer because there's something wrong? It sounds like in your case, you went and killed the node and found out they ran faster elsewhere, which makes it seem like it really, yeah. So then that's where speculative execution would help. But if your tasks actually take longer, what it means is then you're going to spin up another copy of this task elsewhere. It's also going to take a really long time, and now you're going to take up multiple resources doing this really expensive task and throw away some of the work. Which is often fine, right? It's a trade-off you can choose.
Would you say Spark has noticeably different fault tolerance characteristics running on like a Mesos or Yarn versus on a native Spark cluster?
So to be honest, I don't know a lot about Mesos. It shouldn't. So maybe one key thing was the external shuffle service. I think there used to be bigger differences, and those have kind of been eliminated. So Yarn kind of was ahead for a little bit. There's a little more development on Yarn. The key thing was this external shuffle service, that if a process died, you still sort of had that Spark's temporary intermediate data saved in a somewhat longer-lived format, right? It outlived the process, it didn't outlive the machine, basically. But that now exists on every cluster manager. So I don't know of any particular reason. I mean, the second question is just, how well do these different cluster managers deal with that? And I don't have enough experience with Mesos. So Yarn actually has a thing for checking disk health, right? So that scenario I gave with a bad disk, like Yarn, and maybe this is a reason why it hasn't been as bad. In many cases, Yarn kind of does some automatic recovery where it'll just totally independently of what's going on in applications, it checks for disks and it does some adjustments. The thing is that Spark cannot leave that to Yarn. Like, it's impossible for a framework to truly to always detect a bad disk. So maybe Yarn was doing a little better than Mesos. I don't know, which might have made it a little better. But the fact is, like, Spark really needed to be doing better, and now it is. So yeah.
So at least one of the bugs that you showed there seemed like kind of a failure to adequately use the type system in maybe the best way that it could have been used.
Are you talking about that exception handling one?
Yep.
Yeah.
And I was just wondering if there were any kind of ongoing efforts within the Spark project or community to utilize the type system in ways that can prevent or guarantee that errors don't occur, whether through the use of like just having return types that are probably not exceptions, or through using things like converged or replicated types or finite state machines to enforce that you will reach some kind of known state.
So I guess the short answer is no. There's nothing. I think there's a couple of different explanations. So one is that though Spark is written in Scala, it actually shies away from a lot of the kind of more, I will say, complex or Scala-isms, like complicated types and that kind of thing. And it's partially to make Spark itself very accessible to Java programmers. Not just at the API level, but to actually bring Java developers into like contributing to Spark. So it's written in Scala, but there's sort of some fraction of Scala which you can, if you know Java, you can kind of squint and you can kind of figure it out. So I don't think there's ever going to be like some very complicated types that are used for that. Now you might say like, well, we could do, maybe there's some in-between solution. The other answer too is like, honestly, those two parts of code were super, super far away, right? I don't know how big this Spark code base is, but they're just like totally, totally different, right? The other code, like the type never even appears between, I don't think there's any return type that goes between those two things. Now, obviously you can say, well, maybe there should be one, right? But it's just sort of like, I mentioned in the beginning that kind of laundry list of all these cool whiz-bang features of Spark. And maybe some of that comes with like, well, it's like the SQL components aren't often added, but like, oh, well, we should change the way take the core stuff and let's change the interfaces so that we get richer types here and there and everywhere. I don't know if I'm giving you an answer which is making me feel very guilty, but I also feel like to some extent it's just given the size of the code base and the number of people that are in it, I feel like you don't want to just like halt the roll and be like, no, we're going to rewrite everything with like proper types and that'll solve the problem for the next year. And no development in Spark other than like fixing types, right? So I don't know if that answers your question at all. By the way, the solution was to use a thread local basically instead of an exception. That's kind of the way that was solved. Yeah, there's one over there. No? No, okay, I guess no more questions. Well, thanks. Appreciate it.